Okay, so last time we started talking about heights. So let's keep going today. So if you recall last time, for a rational number q in q, we sort of talked about the usual Archimedean absolute value, q infinity. And then we also have the p-adic absolute value, qp, for every prime p. And we define the height of A over B in lowest common form to be, the logarithmic height was defined to be log of the max of A and B. So what I want to do is I want to give a more sort of canonical interpretation of this height in terms of absolute values. And so we do that as follows. So first, it's really convenient to introduce the function log plus. And log plus goes from the, well, it's nice to think of it as going from the sort of non-negative real numbers to the positive real, to non-negative real numbers, that's right. And what it does is it takes the number alpha and just returns the maximum of log alpha and 0. Okay, so if you're less than 1, you get 0 back, and if you're bigger than 1, you get log back. And so then the claim is that the sum over all valuations v, so v being either a prime number or infinity, so v prime or infinity.
Since we're restricted to only non-negative reals, is absolute value necessary?
Sorry, one more time? Oh, no, I guess it's not. Thanks. I guess it's not. So if you sum up log plus of the v-adic valuation over all guys v, then this gives you the logarithmic height of q. Okay? And so you have like a nice algebraic way of thinking about the height of something. So just before we prove this, it's not hard, but note that by the product formula, what does the product formula say? It says that the product over all v this norm is equal to 1 if q is not 0. Right, if you look at a over b and you multiply over all these guys, then you can show that this product is 1. And so another way of saying that, i.e., if you actually sum the logs, what you get is 0. Okay, again, if q is equal to star. And so the height is sort of saying, don't do the logs, only take valuations that help you. And that'll give you the height. Okay? Alright, so let's prove this. So let q be a over b in lowest common form. Now if you sum over primes, log plus of the p-adic valuation of a over b, what you get, well, you only get something when this is bigger than or equal to 1, and that's only bigger than or equal to, but it's bigger than 1, sorry, otherwise you get 0. And it's only bigger than 1 when P divides B. And so you just get the sum over P over prime to divide B. And if P to the n is the exact power of the prime P dividing B, what you get here is P to the n. And so this gives you n log P. This is the contribution for prime P. So if you sum n log P over the primes P, where P to the n exactly divides B, this is exactly equal to log P. Okay? And now, so if you look at the left-hand side here, so the sum over all V of log plus A over B V. Well, first of all, it's this sum, which is log B. And then you got to throw in the infinite place. And so that gives you sort of log plus of the Archimedean valuation. So you get max of log A over B, comma 0, right? Sorry, B can be negative, I guess, so I should put absolute values here. In case now you just take the log inside the max, and I get max of log A over B plus log B, which is just log A, or 0 plus log B, which is just log B. Which is the height. Okay. Questions about this? I'm just sort of tracing definitions. All right. Okay, so let's record some sort of properties of the height. So a bunch of these, but let's record the ones which are most useful. So first of all, if A and B are in Q, then you have log A plus B with this P here is less than or equal to max log AP log BP by the non-Archimedean triangle inequality compared to the absolute value. So it's hard to show because of this. You can put log pluses instead of log. It's good. And so as a result, because these guys are positive, you can replace the right-hand side by the sum. Prime number is P. Okay. And now for the infinite valuation, so if you look at log plus, we equal to the Archimedean norm. Now we can use the Archimedean triangle inequality. So this is the most log plus of twice max A infinity B infinity. Right? Now log is additive, but log plus is this max thing, so log plus is sub-additive. So this is at most log 2 plus log plus of max A infinity, B infinity. Now again, modulus is positive, so we can replace this by the sum. Okay, so what's the point? Now if we sum up over all primes P and over the infinite place, what we get, summing, you get the height of A plus B is most of the height of A plus the height of B plus the sort of little annoying log 2. Okay? And then sort of more generally, you can show that if you sum up R different rational numbers alpha, you get at most the sum of their height plus log of this R. The same argument over here with the non-agreed going on equality here and the argument. Okay? So height is ablative up to the sort of explicit term. Okay, so that's one property. Second property we have is that if we look at so log of A times B, this is literally equal log A plus log B, because the periodic evaluations are multiplicative. So as a result, if I put in log pluses, I throw in some maxes. So again, it becomes an inequality. And then if I sum, I get height of A times B with most of the height of A plus the height of B. That's the second property. These are sort of things we want, right? If we think of the height as an arithmetic complexity, we want to be able to control the complexity of A plus B and A times B and things like that in terms of the complexity of A and the complexity of B. So the third property is that the height of A is equal to the height of 1 over A. Okay. So this is sort of obvious from the height of A over B is max A, max B perspective. They're just flipping A and B. But just to see it from the log plus definition, what you get is that the height of A is the sum over all P of log plus AP. And so which is sort of the sum over all P of max of log A B and 0. Which you can write in the following way also. What I'm going to do is I'm going to subtract from each term the periodic valuation of A taking its log. Now if I sum these over all p, I get 0, so I haven't to change the expression by the product formula. And now I'm going to take this inside the sum, so I get max of 0 and minus log a, which I can think of log 1 over a. And this is the height of 1 over a. Okay? Sorry, this should be a little sum of log v.
Okay, and the previous one as well.
Oh, and the previous one as well. That's right.
I thought suddenly infinity became a problem.
No. I mean, sure. But
well, some people would say so.
right. Yeah, there's v's everywhere. Okay. And so then once you have this, so more generally, you take any integer n to z, and the height of a to the n is just n times the height of a. Okay, so you need to show for positive integers, and then after this guy should scale, for minus 1, we just show it. Alright? So that's the height for rational numbers. So the height for sort of rational numbers is useful, and we'll often restrict to that case. It's also useful to have the height for algebraic number fields, which are sort of extensions of Q, but it's sort of a different level of useful. So we want to extend the height function not just to an algebraic number field, but to all of Q1. Okay, simultaneously. So I'm able to compare algebraic numbers without first fixing which number fields are in. And that's substantially tricky. You gotta be careful with how you define things. And we sort of want this because even when citing reducibility, our number field is not fixed, we're sort of going to a degree is going to infinity. So how do we do that? So suppose you have, first of all, some algebraic number field, which is an extension of Q. Right? So we can essentially take, that's the last one. Okay. We can essentially take this definition and extend it to K, because we have primes in the algebraic number field, and we have Archimedean embeddings, and so we can take the same definition. But we're going to do that, but we're going to be a little bit careful with how we normalize things because we want the height on K to restrict it to Q to agree with Q. We sort of want it in the end to depend only on the algebraic number field that we have. So, take Nk to be the set of sort of finite primes in the ring of integers, finite primes in K, and Archimedean primes, so and embeddings of K into the complex numbers. Alternatively, you could think of Mk as just sort of the set of completions of K, a complete topological field. Okay? So then, if you have a prime, let's see, so if V is in Mk, so V is some valuation of K, then V lies over exactly one prime in Q. Either V is sort of finite, and it divides exactly one prime on finite prime, or it's infinite and it lies over the infinite place. So then you can say that V divides W for W. Valuation of Q, so one of these primes. And so the definition we'll take for the absolute value is xv is defined to be, so what we'll do is we'll take a new definition, but we'll somehow normalize it appropriately. So we'll take the norm from the completion of L at V to the completion of Q at W. There's either the p-adics or the real numbers of x to the power. Sorry, this is a k, no L. The power of 1 over the degree of k over q. And so whatever that is, sort of, if you're comfortable with algebraic number theory, then it is very well done. If you're not, it's not exactly so important. So what's true, what's going to be useful for us is the following thing. So first of all, if you sum over all v's, dividing a certain w, so over all extensions of a given valuation, with this definition. Of log xw, you get log xb. Alternatively, if you multiply all of these, you'll get this one. That's going to be important for us. So as a corollary of that, you get the product formula holds. Sorry, this is v. This is w. This is if x is already in q. And as a corollary, if you sum over all v the log of the v-adic norm of x, you get 0. Maybe it's not a corollary, it's a separate fact. Okay? So it's sort of, and then we're going to define the height of x to just be the sum over all valuations in the same way as before of log plus v-adic norm of x. Okay, so, yes. Sorry. Okay, so this is sort of all pretty fast. So what's sort of going on here? I'm going to give an example in a second of these sort of extensions and stuff. What's sort of happening is that you have a choice of picking a valuation. And you can sort of see this even on Q, where I sort of skimmed over it. So if you look at R, look at the field R, then you have the usual valuation. So this guy is sort of an absolute value, is a norm. Sorry, what I mean? It's a multiplicative norm. But so is the following function. So is the norm to the power of R for any R which is less than or equal to 1. Okay, if you look at this function, then it's still subadditive and it's still multiplicative. And so, in some sense, this norm is just as good as this one. And likewise, this guy for R less than or equal to 1 is the norm on Q. So it turns out we can sort of pick these compatibly to make the product formula work out. And so then we do that with a concrete choice that we use. That's a fact of global algebraic number theory. It's not something you see just by looking at each one individually. Each one of these sort of as good as they can be. So then when we go to an extension of Q, and our field K, once again we have sort of maximum norms we can use, and we can take it to the power of R for any R most 1. And what we do is we're sort of scaling them down appropriately in order to make sort of agreement from a number field K with what we define by Q. Okay, so as an example, to see sort of what's going on, instead of the field K, we just Q adjoint like 2 for 2, and let's see what's happening at sort of one Archimedean place, and one non-Archimedean place. So if we take W to be infinity, if for Q we take the Archimedean embedding, then we have 2 primes, sort of 2 Archimedean primes above this. We have sort of V1, which takes A plus B root 2. So if I think of root 2 as the positive square root now, I can just look at the sort of usual absolute value of A plus B root 2. And I have a second prime V2, which I can look at the usual absolute value A minus B root 2. Okay. But what we're going to do here, sort of what the previous definition I wrote down amounts to, is we're not going to take these absolute values. What instead we're going to do is take these to the power of 1/2. Okay, because K is the degree to field over Q. So to the power of 1 over the degree is equal to the power of 1/2. And so the reason we do this is that now, so if sort of A is just a rational number, then if I sum AB1 with AB2, what am I really getting? I'm getting the usual absolute value of log to the power of 1/2, and I'm getting it twice, once for each embedding. And this is just the regular absolute value of A. Okay, so I get this formula that I wrote down earlier. So that's sort of what it looks like an infinite prime. And then if I take W to be a finite prime, so the prime 2, there's one prime lying above 2, which is just Q root 2. And then what I do is I define the prime sort of V above 2. It's unique. And what it does is it takes A plus B root 2 to the maximum power of root 2 dividing these guys. So I'm going to define it to be root 2 to the sort of why I divide it as minus min valuation of A, and sorry, twice the valuation of A, and then 1 plus twice the valuation of B. Right, so there's some power of sort of 2 dividing A, and twice the power of root 2 divides A. And likewise, you have some power of 2 divides B, and twice that power of root 2 divides B. You're multiplying by root 2, and so you get this plus 1. This sort of tells you the power of root 2 dividing this guy. Then it's the same definition as sort of before. And now because we have exactly 1 prime above 2, we actually take this guy, we don't raise the power of 1/2 or anything. So then if we just take a number A which is in Q, then AW thought of as valuation in Q is the same as AB. Okay? Okay, let's have an attempt to describe sort of what goes on for other algebraic number fields. So one thing which sort of comes out of this is that if you take alpha and q bar and sigma any element of the Galois group, because we define things so intrinsically, it sort of follows pretty immediately that the height of alpha is the height of sigma applied to alpha, of all the conjugates of a number with algebraic number of the same height. Okay? Alright, so that's, something can prove in the same way are those three properties that I wrote down for the height. So it's sort of subadditive up to this log 2 factor, or log r. If you're summing r different guys, it's submultiplicative, and height of alpha to the n is n times the height of alpha. Alright, any questions so far about the height? You know, those rather fast. Okay, so pretty soon we'll write a much more concrete. This is sort of a nice description because it's very, very intrinsic somehow with its absolute values, but pretty soon we'll write a much more concrete definition of the height in terms of its minimal polynomial. But for now, let's sort of prove the height is a good notion of complexity. So let's prove some basic finiteness lemmas. So for a positive integer d, and a real number m greater than 0, and there are finitely many algebraic numbers alpha and q bar with height of alpha at most m and the degree of alpha equal to d. Okay? So it's sort of obvious from the concrete definition that if you just take d equals 1, this is true, it's just saying you're a over b, where a is the most m, b is the most m. In fact, to get the sort of much stronger finite statements, where you can look at not just a fixed number field, but all number fields of a given degree at once. And so the proof is something of a standard trick in this subject. The proof is you look at the minimal polynomial of alpha, and you sort of want to show that you only want to finitely many things. So what you do is consider, so let alpha 1, alpha 2, alpha d be the conjugates of alpha. And then you write p of x as just the product of x minus alpha I. And because we're taking the product over all the conjugates of alpha, this is not necessarily in integers because these aren't algebraic integers, they're just algebraic numbers, but it certainly is a polynomial with rational coefficients. Okay, and let's sort of name the coefficients. x to the d times a sub I. X to the I times a sub I. So these a sub i's are rational numbers, and the idea is to show they have bounded height, which means there's finitely many of them. We know the result for okay, and so if we look at sort of a sub I for any given I, what is it? Well, it's the sum. So I guess it's minus 1 to the I times the sum over all subsets of 1 to d of side I of the product of all the guys in that subset, literally expanding out polynomial. These are the elementary symmetric functions. And so as a result, if you look at the height of a sub I, by subadditivity, it's at most sort of log of d choose I. So that's how many guys we're summing. Plus the sum of the heights of each of these. So again, there's d choose I terms in the sum. We know that the height of each alpha j is at most m, and heights are subadditive. And so this is this guy times m times I. Whatever. So whatever this number is, it's some finite number depending only on m and b, but b is sort of fixed. Okay. Now, since the AI are rational numbers, we know the result of rational numbers, so there's only finitely many possibilities for each coefficient, which means just finitely many possibilities for this polynomial, and just finitely many possibilities for alpha.
If you turn this into a quantitative statement, how far out would it be?
It's a good question. Not so far in terms of m, but probably pretty far in terms of d. So, think about it. Yeah, in terms of m, it's actually pretty close, because if d is, like, you can think of d is 1 more generally anything, then you literally just have bounds the coefficients of the polynomial to some constant. But if you actually care about degree growing, well then this is sort of horribly inefficient and small. Alright, now a nice thing about this is you can connect up roots of unity in the theory of heights. So note that if alpha to the n is equal to 1 for some positive integer n, then 0, which is the height of 1, is also the height of alpha to the n, because they're equal, and this is n times the height of alpha, and so as a result, roots of unity are algebraic numbers of height 0. And so in fact it turns out these are the only algebraic numbers of height 0. So if height of alpha is 0, this is equivalent to alpha being a torsion point, dealing with q bar on the right, and q bar star. Okay? So the proof is sort of a nice trick to sort of do this, but backwards. So if you look at p of x, so consider the minimal polynomial, not just of alpha, but of alpha to the n, for every n. En of x, the minimal polynomial of alpha to the n. what is this polynomial equal to? Well, for that alpha 1 through alpha d be the conjugates of alpha, then Pn of x is equal to the product I equals 1 to d of x minus alpha I to the n. Okay. You have to be a little careful. I mean, it's not strictly true because if you take like squares, then some of these may repeat. So you might have a smaller degree of the polynomial. But it doesn't matter. I'm going to define P of n to be this in the case. Okay? So again, this is in keywords right next. Let's write it as a sum over j of x to the j times aj. Let's put an n up here to remember that this is the nth guy. So now, as before, we have the height of ajn is sort of bounded above by the heights of these guys, which are 0. So in fact, in this case, the height of this guy is at most log of d choose j. Okay, because the height of all of these guys are 0. So this is same way as before, the subadditivity. And so therefore there's finitely many possibilities for these guys. So therefore the Pn must eventually repeat. Right? Because for every n you get sort of one finitely many polynomials, and so certainly two of them must be the same. Okay, so assume that like P n equals P n plus m, so that's for n bigger than 0. So what is this saying? Well, it's saying they have the same roots, and so you must have alpha 1 to the n equal to one of its conjugates. I can write this as alpha 1 to the n equals sigma times alpha 1 to the power of m plus m. Right. And in my proof, I incorrectly assumed n was 1, which made things easier. So give me 1 second to fix this. No, sorry. This is slightly incorrect. I can just write P of n is P of nm for some nm bigger than 0 and m bigger than 1. In fact, for some nm bigger than 1. Yeah, just looking for P of 2, P of 4, P of 8, P of 16, so forth. Two of them are the same, and then one divides the other. So we can set it up like this. So Sorry, this is much nicer. So in other words, alpha 1 to the n is sigma alpha 1 to the n to the power of m. And so then if I look at this, so if I do it again, what I get is alpha 1 to the n is this whole thing, so plugging it in, we get sigma squared of alpha 1 to the nm to the power of m, which is sigma squared of alpha 1 to the nm squared. And so if you keep going, you get alpha 1 to the n is sigma to the r of alpha 1 to the nm to the r. So then if we take r to be the order of sigma, so if sigma to the r is equal to 1, what you get is that alpha 1 to the n is alpha 1 to the n m to the r, which means that alpha 1 is a root of unity. Right? Sorry, this last part I made it seem much more complicated than it actually is. The point is that the roots sort of have to cycle. You look at the power, that set eventually has to cycle. So you could actually say alpha 1 to the n is alpha 1 to the n, you'd be done. It's a little trickier because you might get a different conjugate instead. But you can only get so many different conjugates. So this is a little bit complicated to your actual time. Okay? Okay, that's a really nice fact. It's sort of the height actually captures the roots of unity. All right, so let me just write down other statements, and we'll prove it next time. So Euler's definition of the height in terms of valuation sort of feels too much algebraic number theory for you. You can actually give a much more down-to-earth description of it. So suppose you have a polynomial P of t of degree d with all of the coefficients integers and relatively prime. So not pairwise, but if you look at all of them together, the coefficients are relatively prime. And assume this is irreducible. Yeah, let's not deal with that unreducible guys. So let's write it as the leading coefficient times the product of the roots. Now we assume it's irreducible, so all these guys are algebraic conjugates, so they all have the same height. And so then what you can do is you can write the height of alpha 1 as, well, times d, as the log of the leading coefficient plus the sum over all of these j's of the log plus of the alpha j's. Okay? So somehow if alpha 1 is an algebraic integer, so this AD is 1, then all you get are these Archimedean guys and the sum, which would be expected. And then to take care of these finite primes, which are kind of weird, they're somehow all recorded out in the leading coefficient. Okay? Right, so next time we'll do this and we'll start on the analog of Lang's theorem for point of small height.